Okay, so, oh, I keep forgetting about this thing. Normally, when we have classes in person, we wait 10 minutes for people to walk across campus to get to the class. I'm not sure if we're supposed to do that in this case. I guess since people are still streaming in, I probably should wait. If you're coming into the class, especially since it's the first class, it would be nice to turn on your video just so that I can get some kind of sense of who everyone is. Normally, this is not such a large class that I can't start remembering people. Okay. Okay. Yeah, people are still streaming in, so I better wait. Matt Coster. Matt, you're there? You're taking this
Yeah, I'm
class.
here. Yeah.
Why are you taking this class? Haven't you taken it already?
No, I haven't,
Oh,
unfortunately.
okay. You're taking it as 1723, I guess.
Yeah, yeah.
They separated the class into two completely different courses, like officially, the graduate level and the undergraduate level, and they each have a Quercus. They each have the entire system. It's very annoying. And I think, and I can never remember which was which, but I'm supposed to grade one class in letter grades and one class in numerical grades.
Yeah, I think all of the cross-listed classes are like that.
Very annoying. Is CS here? Who's CS? You should put your name just in case. And why are some people listed as guest, whereas others are not?
It means they haven't linked their Zoom account with the official like U of T Zoom account.
I see. Yeah, it's exactly the reason why I didn't require people to be authentic.
You're muted, Professor. You're muted.
Hi. Yeah, you can hear me now, right?
Yeah.
Okay, so I just blew a fuse. It'll take me a couple of minutes to get my internet back online. Just stand by.
Yes.
All right. Is this working? Okay. Wow. Okay. That's strange. There must be one or two extra things on my power system and just blew the half of the floor. That's funny. Okay, wait. I had all my stuff open here. 1 second. Okay, everything is back online. All right, let's begin. Sorry for the delay. So welcome to Quantum Mechanics. For 2021. I didn't think I was going to be teaching this online, but that's how it is. So the Quercus is open. The syllabus is available there. That's the official syllabus, but there's also the web page. The web page doesn't have all of the marking scheme information and so on. Basically, I don't want to spend too much time on this. I want to start the material. So so the basic idea is that there will be 5 assignments, 6 assignments, and they will be worth 80% of the grade. And then there are 20% which I marked as quizzes. So the idea of the quizzes is supposed to be that I'm going to assign reading, and the quiz will be a very brief, just a kind of check on whether you did the reading or not. So, I mean, I don't. I mean, it's a device which is supposed to incentivize you to or motivate you to do the reading. That's it's for your benefit. I don't really. It's not going to affect me. It's really just for you. So that's 20%, and that's it. These. Oh, that's a good point. I forgot to start the recording. So there will be a recording of this, which will be on. Oh, I think that actually the live stream never stopped. Oh, so all of that is captured. The moment where my power died is captured on YouTube. That's excellent. Okay, great. And I'll post the links for those once they're available. And also the notes that I write during the class will be made available. Okay, and then the most important thing is the thing about books. So, I think the best book still to use for the material for most of the material I want to present is in Voigt's book. It's very clear. He's a mathematician. It's not overly mired in mathematical kind of sophistry. It's pretty down to earth and explained pretty well. So, and the book is available online. So that's the main text, and that's what I'll assign reading in. But the other books are also very good. They're more they go into more mathematical complications, which is good, but it makes it a little bit more difficult to read on a first round. One of the I kind of have a dream of teaching the course using only Dirac's book, which is which is not easy to do because he doesn't really do many calculations, and he doesn't provide any exercises, and it's not really a textbook. It's more like a speech, a very long speech. But it would be nice to teach the course based on that book and to explain everything that he is saying. I really admire this book. I think this book is the most important book ever written on quantum mechanics. And especially because near the end of the book, he makes some very, and this is very unusual for Dirac, he makes some very wild, or let's say dreamlike speculations about things that he doesn't fully understand. And that it turned out to serve as a guide for the future development of quantum field theory. And then I think the last book on the list is that would be my second dream, is to teach the class based purely on that book, which is a book written by Feynman and one of his, I think, postdocs, which is an extremely difficult book. I don't think I've met anyone who read the entire book, who understood everything in the book. But I will not be doing that. That is not yet feasible for me, or for you, or for anyone at the moment. So, but I encourage you to look through them and to read, try to read them, read pieces, and maybe use them as a guide. I put some articles which have material that never materialized in books. The first is an extremely famous and increasingly important paper of Atiyah. When he wrote it, it was considered to be one of his lesser works, but it turns out that the importance of it has only grown, and it has grown so large now that it almost eclipses his other works, and that that is closely related to the famous paper of Witten, listed after. And then there's a very interesting paper by Bender and Wu from 1969, I think, if I'm not mistaken, the Enharmonic Oscillator. We will talk about this paper in the last part of the course. This paper, I think, is after the works of the originators, after the works of Dirac and Heisenberg and Bohr and all the famous originators of quantum mechanics. I think this paper is probably the most important paper ever written on quantum mechanics. And we'll see why as we get into the material. Okay, so basically basically what we're going to do with the course is we're going to start with. So let me just switch over to. Okay, actually, so that's the end of the syllabus part. I'm going to say something about the content of the course now, but if there's any questions about like the technicalities of the course, please ask them now.
Professor?
Yeah.
I'm checking Quarkus and I haven't seen the syllabus yet.
Have you clicked on the word syllabus?
I can't find it. It's not there. So
It may only be published in the undergrad portion. It may not have been published in the graduate
No,
side.
it should have been. Let me check.
Oh.
1 second. Undergrads, have you seen the syllabus on Quarkus? Okay, let me just check.
I found it on your personal webpage.
2021. Okay, wait, 421. It's published. Have you clicked on syllabus on the left-hand side? One of those things is syllabus.
Yeah, it just shows home announcements, grades, and library resources on the left-hand side.
Oh. Why are they not? Oh. Not visible to students. Okay. Settings. Okay, wait, let me just solve this quickly. Okay.
If you go to the navigation side on settings.
Yes.
I think you can just drag it up.
Oh, on the navigation?
Yeah, when you go to settings, there's a tab that says navigation.
Yep, I see it now.
Mm-hmm.
And syllabus. But what do you see in terms of activation there on that page? Drag and drop items to reorder them in the course navigation.
Yeah, so you should see the list of all those like pages. You click on syllabus and you drag it to the top.
Yes.
And somewhere you probably have to save. Yeah, you save and then we should see it.
Oh, thank you. You're right. Yeah. How did you know this?
In my TA webpage.
Okay, wait, let me do the other one. Foundations, 1723. Settings. Okay. Now you guys should all see the syllabus. Okay. So, right. So basically what we're going to cover in this class, we're going to first talk a little bit about classical mechanics, and especially the Hamiltonian formalism. You can see what I'm writing, right? Then we're going to talk about the foundations of quantum mechanics. And then we're going to talk about examples. So there's going to be the simple harmonic oscillator and a couple of other big ones. So there's the hydrogen atom. And there might be a few others like the anharmonic oscillator. Okay, and we also need to understand the way that symmetries are incorporated into classical and quantum mechanics. Symmetries are the main theme of the entire course. Symmetries and conservation laws. So this means that we're going to need to learn about Lie groups, Lie algebras, and representations of these. This will be the main mathematical tool. We're going to talk about Hilbert spaces, finite versus infinite dimensional. We're going to talk about quantum computation. And we're going to talk about perturbation theory. Those are the main topics. Any questions about this? Any requests for additional topics? By the way, are there any chemists here? No chemists? I always like having a chemist in quantum mechanics because chemistry is probably the best place to apply quantum mechanics. Okay.
Professor?
Yeah.
Are we going to cover Fermi's golden rule?
Maybe not. I mean, that's one. There's probably 20 things of the same nature that you could ask about. So yeah, I mean, I'm not going to go to discuss all these different rules. So we'll see when we get to yeah, in fact, the discussion of fermions in general, it's a good question about whether normally we don't have time to discuss fermions at all. It just reminds me of that. Okay, so let's when we do perturbation theory, we might cover that. Okay, so let's. Oh, and also the office hour is after this hour, and yeah, so every week we can discuss during the office hour. Okay, so I want to talk about classical mechanics for a little bit. Maybe this class, this week, I want to talk about classical mechanics. Okay, so part one is a description of classical mechanics. I'm going to try to do a vast simplification and boil it down to some very simple aspects. Okay, so first of all, there's the Newtonian point of view. Okay, which looks like this. So I'm going to kind of try to simplify it and distill it as much as I can. So we have a point particle moving in a force field. Okay, and this will have a position which depends on time. Time dependent position. That's the trajectory. And the question is, if I have a particle and if it is in a certain environment with a certain set of forces, what will the trajectory be for this particle? So, we need a space where the particle is moving. So we can take that to be r to the n, for example, and the position is a point inside this r to the n. The force field what is the force field? It is it's a vector valued function on space. Okay, so this has n components, which indicate the direction and magnitude of the force. So we have our space, we have some vectors. There's a vector at every point in space. This is f of x. So this is a point x, and this is the f of x vector. Okay, and then we have time, which is just r, with coordinate t. So here, when I said position, you should think that this is the coordinate for the space. So we have a t coordinate for the time. And the trajectory of a particle, what is it? It is a map from the time to the space. It takes each real number, which is the time, and it takes it to a point in space, which depends on the time. Okay, and this particle has a mass. The mass is a real number, which is, well, in classical mechanics, should have a positive mass. Okay, so we have a space, we have a force which depends on the space, the position in space, and we have a trajectory of a particle, which is a map from the timeline into space, and this trajectory is the trajectory of a particle which has an associated quantity called a mass. It's just the real number, which is a kind of characteristic number. It's a characteristic or a property of the particle. And the law of motion, is Newton's law, which is saying that that if I look at the force, if I evaluate the force at the position where the particle is, that should agree with the acceleration. So d2 by dt squared of x of t.
Just a quick question. Are we taking the force field to be fixed in time?
For now, yes.
Okay.
There's all kinds of complications that you could introduce, but I'm not, for the purposes that I need this for, I only need the simplest format, and then we're going to generalize that. Of course, the force could be time dependent. You could have multiple particles, etc. But this is the Newtonian approach. You have a space, you have a trajectory, and you have a differential equation. This is a second order differential equation. It's actually a it's actually a system of ordinary differential equations. And that's what you need to solve. And we'll do an example shortly. I'll probably on Friday I'll do a couple of important examples. Okay, now there's a different formalism. So I'm going to move away from Newtonian formalism. Is this okay? So we'll see more examples, but this is the basic input. You need to be given. This is called a vector field. On Rn. Okay, so the force is a vector field on Rn, and this is called a path or curve, and we would like it to be differentiable, right? Because we need to be able to apply the law of motion. So we would assume that this is, let's say, C infinity. so that all the components of the trajectory should be differentiable in time. So all these functions should be differentiable. Each one of them should be differentiable. Okay, so so note that yeah, okay, so maybe the important thing to realize, because of the fact that this is a second order differential equation, is that if you want to find, like, there are many trajectories which satisfy the law. For example, if I start here, if I start at a certain position, then the question is, well, how do I use the law to find the future trajectory of the particle? Well, the law tells us that the acceleration, or the change of the velocity, is given by the force. So the force is telling us that if the particle was moving in this direction with a certain speed, so if this was the velocity of the particle, then like, for example, here, suppose that at a certain time this was the velocity of the particle. Okay, the fact that the force field is pointing in this direction, that is telling us how this velocity should change in the next time step. So that in the next time step, roughly speaking, the velocity will change. And so that means that the trajectory will be forced to curve in the direction of the force. Okay, so what is this telling us? It's telling us that, and this is the case for all second order ODEs, is that if you want to solve the system of ODEs, you need to be given an initial condition. So to solve this means to find a trajectory satisfying the law. And there are many solutions. Okay, because there would be, one solution would look something like this, or, sorry, that's not what I meant. For example, let me put a force field which is more realistic for real life. Force field like this, suppose. A constant force field pointing in the -z direction. So there would be a trajectory that looks like this, for example. In which you can see that at every time, the velocity is as shown. And as time progresses, the velocity vector is basically forced downwards. So this velocity vector here is being, in the next time step, will be forced to move down. Okay, so, and there will be other trajectories like this, and like this, and so on, and like this, right? So there are plenty of trajectories. And these trajectories, if you wanted to pick one out, if you wanted to select one, the way you do that is with an initial condition. So to get a unique solution, we specify an initial condition, initial data. And that initial data consists of a position, an initial position, and and an initial velocity. The dot just means d by dt at t equals 0 of x of t. That's what this x dot means. So because it's second order, that means that we need not only the position, but also the velocity at time 0. And then the future trajectory is determined by that. I'm sure that you're all familiar with this, but if there's any questions, go ahead and ask. Clear? Okay. So there's another point of view. There's another way of thinking, which is equivalent, an equivalent formalism, the Hamiltonian formalism. From a mathematical point of view, what the Hamiltonian formalism is a very simple trick, which is to convert the second order system to a first order system. Okay, so in other words, instead of writing f of x is equal to m x dot x two derivatives on x, what we could do is give a name to the first derivative, and then say that f of x is equal to p dot. And we need to include the mass, so we'll put it in here. So this is called the momentum. It's a new variable, which from a mathematical point of view is introduced so that we can convert a second order ODE to a first order system of ODEs. And in fact, this is a system of second order ODEs, and this is a first order system. They're both systems, but the number of unknowns is doubled in 2 times the number of variables. So the variables here that you're trying to solve for are x and p. Okay, so this means that we double the number of variables used to describe the state of the system. We go from x to xp. And now the advantage of this is that okay, so let me just try to explain. I'm sure that you've seen this to some extent, but it's worth kind of explaining it carefully. That now the way that we interpret this is almost as if our initial space has now been de-emphasized in preference for this doubled space. This doubled space has a name. So when we take Rn cross Rn with coordinates x and p, okay, this space is called phase space. Okay, and because we have a name for this doubled space, we kind of need to give a name to the original space. The original is called the configuration space. Okay. And the advantage of this is that we can, well, we can interpret this first order system in the following way. So see, like what this thing is saying is that if you know the value of x at a certain time, and if you know the value of the momentum at that same time, so if you know the value of x and p at that time, then this system tells you how it should change in the next time step. It gives you the change in the next time step of these quantities. So in other words, at every possible x and p, for every point in phase space, okay, there is a vector at that time which will tell us how p and x change in the next time step. So let me just explain. So so we know from the law that x dot, and if we look at this, is going to be m inverse p, and p dot is equal to f of x. So if I want to know how this point, this initial point, is going to change in the next time step, what I have to do is look at the value of p itself. Let me just move my text here. So I look at the value of p, okay, and this is saying that the x derivative is given by a factor multiplied by p. So that means that there will be the x component of the vector, and there will be a p component of the vector. So, which will be the value of the vector f. So at this point, there will be there will be some value of f of x. That will be a vector in the first Rn, and that f of x now is going to be the derivative of p, and so that will be put into the p direction. These two, we'll take the sum of them, and we get the way that the point in phase space should change in the next time step. So this is representing the right-hand side, telling us how x and p should change in the next time step. I do not, so that means that, yeah. So this is it's more of an initial value problem. So the advantage, let me just spell it out. So the advantage is that if we know the initial state as a point in phase space, the future trajectory is uniquely determined. Okay, so as soon as I know that I'm at this position, then I will determine my future trajectory. I do not need to know my position in phase space as well as the velocity in phase space. That is not necessary. I only need to know the position in phase space, and then the future is determined. This is not surprising because the position in phase space is the initial position and the initial velocity anyway, right? We're doubling the variables in order to include the velocity or the momentum as one of our variables. And so if you know the initial position and velocity, the future determination is unique. Okay, so the state of the system is at time t is x of t, p of t. So there's a difference now between the position, which is a point in configuration space, and the state, which is a point in phase space. Okay. So let me just say one thing to conclude. The Hamiltonian equations, the Hamiltonian Law of Motion, which is just this x dot is p and p dot is f. Okay, it defines that's what I just explained. So you see what I just explained is that the right-hand side here is giving us two quantities, which are vector quantities, which when summed together give us a vector at each point in phase space. A vector at each point in phase space, which is a vector field. So the phase space has a vector field on it. So you might say, well, okay, what's the difference? So what? We on space, we had a vector field. That was the force. Okay, but the problem is that, as you can see with the force, it's more difficult to figure out how the particle trajectory is going to behave, right? The force vector field is not pointing along the trajectories. That's not how Newtonian mechanics works, right? This vector field is influencing the trajectory, but it is not tangent to the trajectory, because this vector field is not telling you how the position changes in time. It's telling you how the velocity changes in time. Whereas in this picture, there's a vector field, just as in the Newtonian method, there is a vector field on the state space, on the phase space. Okay, but the difference here is that, however, so to find a trajectory, to find a solution to the system, we find what's called in mathematics an integral curve. So I'll give this vector field a name. I'll call it X, and it's called the Hamiltonian vector field. Okay, and to find a solution to the system, we have to find what's called an integral curve. And that is, it is a curve, X and P. It's a curve in phase space. I'll call it gamma, such that the derivative of gamma at time t is equal to the value of the Hamiltonian vector field at that position. Okay, this is just a rewriting of this. So if I look at this force field, the way that my solution would look, if I started here, say, and I don't need to know the derivative at this point in order to proceed, I just need to know the position in phase space. It tells me that in the next time step, it will move up. And then in the next time step, it will move like this. And so it will remain tangent to the Hamiltonian vector field. Okay, so you could say that the advantage of the Hamiltonian formalism is that it makes absolutely clear what the trajectory emerging from every point in phase space is, because the vector field is provided to you, and that vector field tells you exactly in which direction to move. Okay, this is all just a reformulation of the standard trick that you learn in ODEs to take a second order ODE and make it into a first order ODE. Okay, and this Hamiltonian formalism is equivalent to the Newtonian formalism, really. So you're not really gaining anything, but it turns out that this way of thinking is extremely useful for understanding symmetries, for doing classical mechanics. And also the funny thing is that this is the formalism that easily generalizes to quantum mechanics. And so when we write our quantum mechanics, it will be in Hamiltonian terms. It will be in first order terms. That's very important. Okay, so on Friday, we'll do some examples of this classical mechanics. If there's any questions, it's office hours now, so you can feel free to ask. Questions?
Professor, I still can't seem to find the syllabus on the Quarkus page.
Okay, yeah, no kidding.
Did you save it afterwards? In the bottom, you have to press save.
Think about your questions while I solve this nonsense.
Some people can find it. Maybe it's the graduate page.
Oh, okay. On the graduate page, it is available already. And then the undergraduate page.
Maybe we just need to refresh our clear the cache.
The cache, yes.
Cache, thanks.
Yeah, it should be working. So if you're does any graduate student have it?
I put it in the chat if you really desperately want to see it.
Thank you. Let's see. How many people? Oh, actually, did anyone notice how many people were here at the maximum?
Yeah, I think it's 40, right?
There were
Yeah,
40
that's what I saw.
today?
Yeah.
Okay.
Professor, I was wondering, do we need for Lie groups, do we need a background in group theory, or it's okay?
No.
Okay, cool.
No, I don't think so. The textbook, the main textbook, assumes no knowledge of group theory, as far as I know.
Okay, perfect. Thank you.
Someone asked whether we could do geometric quantization. Well, that would be great. That's not, maybe I'll try to fit it in. Yeah, give you some idea of at least how it works. That's something that I work on. Maybe I should have explained. Anyway, I'll say more about what I work on Friday. But is there anyone who has any concerns or questions?
Are we like also gonna touch on like introductory QFT, or is that not gonna be possible?
Well, so quantum mechanics is a quantum field theory, and perturbation theory is basically the same, roughly speaking, whether you do it for quantum QFT or QM. So for anything that you might be interested in, which most people are interested in Feynman diagrams because they like looking at little pictures and things. So Feynman diagrams are equally valid for quantum mechanics as for QFT. There's no major difference. So we will be doing that.
Thank you.
You're welcome. And then someone asked, Ami Reza, are you there? Does your microphone work? You can talk. Why not talk? You're afraid. Quantum information theory. We're going to do a little bit of quantum computing, but properly doing information theory, that's beyond the scope of the course, like Shannon entropy and stuff like that. No, we're not doing that. Where is everyone anyway? Kunal, where are you?
Here.
In Toronto?
Oh yeah, I'm in
You're
Toronto.
in lockdown?
Yep, been stuck in my one-room apartment for a while now.
I can't imagine if it was completely silent, very highly restricted, but you can still go out and exercise, so that's good.
Oh yeah, I've even bought some like weights, a yoga mat and stuff like that to keep myself busy.
Yeah.
Taped off different parts of the room to sort of like, one part just for relaxation, one part for work.
That's right. Yeah. Everyone is becoming an expert at self-sufficient, entertainment and lifestyle. Or is there anyone who's not in Toronto? Luke, are you in Toronto?
I'm just north of Toronto in Vaughan.
In Vaughan. Okay, yeah. Jai?
Yeah, I'm in Brampton.
In Brampton. The Toronto crowd. Okay. Neo?
I'm also in Toronto, and I run around Queen's Park every day in the morning.
Oh, really? Oh, I go there quite often to run around Queen's Park. Yeah, that's where I like to go.
Oh, cool. If I see you next time, I'll say hi.
Yeah, good. Is that your real name, Neo?
Yeah, it's my name.
That's cool. Yeah, famous name. Matthew Kronberg.
Oh, I'm in Ottawa.
In Ottawa.
Down the way.
The nation's capital. Wow. Where all of the lack of planning happens.
That's right. Yeah. If I knew how to fix it, I would try. But...
Say, your microphone isn't very good. I can't hear you.
Oh, sorry. I just said if I knew how to fix it, I would try.
Right. I'm sure that there's a lot of planning. There's a lot of failure of plan. See, I think that in Ottawa, people think that they're not planning anything, that they're just incompetent. But they might be incompetent, but I think that they actually are trying to plan a lot of things, and there's a lot of failure. I think there's a lot of failure in at the private sector and the public sector, but I think that they don't want to tell us all the failures, with the vaccines and the rollout and all that. I think that they're very desperately trying, and they're trying hard, but what they should do is they probably should tell us about all the failures. so that we don't assume that they're doing nothing, which is what I think most people are assuming.
Yeah, there's like a little song and dance where the premier says that the federal government's messing up, and then the federal government says the premier's messing up. You usually caught in that little cycle there.
Yeah, I think that the reality is probably very complicated because they do have, you know, all these civil servants. They're all working very hard to organize everything, but they keep it very quiet. Okay, so if there's no questions, I'll just close it here and we'll resume on Friday.
Oh, actually, I have one question.
Yeah.
Can you hear me?
Yes.
Just the reading, or do we have readings for this? Is there a reading list that hasn't been posted, or is it just?
I'm going to put the reading up as announcements
Okay.
with the assignments. So when I give you the first assignment, the reading will be clear. But what you should just do is start with the main text and read the beginning.
Okay. Okay. Thank you.
It's a very nice introduction and first chapter. You can just start with that.
Okay.
He's a kind of famous guy because he was he's a very outspoken anti-string theory person. He's a kind of hardcore quantum field theory person from the old school who doesn't believe in string theory, which I mean, I don't have the same view as him, but his quantum mechanics book is good. All right, everyone. See you on Friday.
Professor.
Oh yeah.
So would the recorded lectures be put on YouTube or?
Yeah, the lectures will be on YouTube, and there's going to be a link.
Okay. Would it be also possible to like embed them into your website or post them on Focus? Okay.
No, they're not really public. I'm not supposed to make them public. I'm supposed to make them available to the students, but not public. I don't know. I might put them on YouTube anyway, but they're just not going to be linked from the web page.
Okay.
Yeah. I'm not even sure if I put them up on YouTube whether I should allow comments or not. That's very dangerous. Okay, see you on Friday. Cheers. Have a good week.